Welcome everyone to my first lecture for Weld 40, Introduction to Welding at Mount San Antonio College. And what we were going to talk about is we wanted to talk about the oxyacetylene flame itself, and then we also wanted to talk about where we get oxygen and where we get acetylene. And before I get into that, I wanted to talk to you about what usually happens the first night when we're welding. And that is you're going to have the metal here, and I have some people that don't put much heat into the metal, and they end up with the filler material just sitting on top of the metal. It's just barely sitting onto it. It's not actually fused into the metal. And what I wanted to tell you is that we want that fused into the metal. We want it tied into that. So you're going to have to get used to putting heat into the metal. This metal that we're welding tonight melts at around 2,400 degrees Fahrenheit. And the flame itself reaches 6,300 degrees Fahrenheit. We're going to talk about that in just a moment. But having a cold piece of metal just sitting on top of the metal isn't going to do anybody good. We're welding, and we want it fused into the plate itself. So it's not uncommon for me to actually take a torch and I'll burn a hole right into the metal. Literally take it and focus it right on the metal and let it just burn a hole, just to show you that it can be repaired for one, but also that we have to get heat into the metal in order to get it fused. So for those of you that are really careful with the torch and just barely put enough heat into it, if it's just sitting on top and you're not fusing into the metal, that isn't what we want. We want to get more heat into the metal itself and get the filler material tied into the base metal itself. So I wanted to start the lecture, and the oxyacetylene flame itself, it was discovered in 1895 by a Frenchman by the name of La Chatelière. The torch that we're using, that was discovered in 1900 by another two Frenchmen, Fouché and Picard. The first torch was actually used in the industry around 1906. So it took them a few years to kind of fine tune it and kind of put things into play. But the oxyacetylene flame itself, it reaches 6,300 degrees Fahrenheit. And the metal that we're using tonight, it melts at around 2,400. So we shouldn't have any issues with heating it up enough. The only thing that would vary this is the actual thickness of the metal itself. So obviously if you have something thicker, it's going to take more time for this 6,300 to heat it up. And the thinner that it is, the quicker it's going to warm up, and you're going to be able to melt it. The oxyacetylene flame varies from 5,800 to 6,300. That depends on the type of flame that you're using. And we'll talk about flames in another lecture, and I'll also demonstrate that to you at the school. I'll show you the carburizing flame, the neutral flame, and the oxidizing flame. So that'll be part of my demonstration. But I want you to remember that this flame reaches 6,300 degrees Fahrenheit. You'll hear me say it a few times. You'll also see it on a test. So anytime you see it on a quiz or midterm, it will be referencing this 6,300 degrees Fahrenheit. So what do we use it for in the industry? Mainly it's for general maintenance. Auto body uses it, repairing of small parts, definitely cutting. We cut a lot of materials still to this day and into the future with this flame. It's used very common in fabrication shops and also out into in the welding projects itself. So you'll all get a chance to do some cutting here during the semester. Also some soldering, some brazing. I'm going to be doing a demonstration on soldering, and you all will be brazing in the class. So you'll get a chance to see how oxyacetylene is used for that. But here's the key. The metal melts so completely that they can be joined without any mechanical pressure. So you might remember the blacksmiths back in the day where they were heating the metal up, and they were banging the material on an anvil and spreading it out and trying to join. They used rivets prior to it. But here we have a process where you can actually heat the metal and actually fuse it together. And if the weld is done properly, it's just as strong as the base material itself. So that's key with what I'm saying, is that if the weld is done properly, that the weld itself will be just as strong or stronger than the base material itself. And that is the foundation of the welding industry and the design and implementation of the welding processes itself. Now, besides welding, oxyacetylene is also used for case hardening, where we're trying to put a hardened surface onto a piece of metal where it might have some wearability, where they use hastolite and tungsten carbide. We actually have tungsten carbide filler rod where you would heat it up and put layers of tungsten carbide on metal, and that's where you have a lot of wear and on a surface, maybe on a backhoe bucket, something that's going to be worn for a while, where you're not, it helps with the wearability of the bucket blade itself, where you're not having to change the blade itself, but you're just wearing out the hard surfacing material on it. But it's used for that, and also stress relieving. If you have a real thick piece of metal that you're welding, where you're putting multiple layers here. When you get into the high carbons, usually it's just the high carbon metals. That's where you really need to play into elevating the heat and then reducing the heat at a slow rate so that you don't get any or induce any cracking into the weld. Because every time that you place one of these welds, it will contract. You'll get some contraction with it. And so, not so much with the mild steels and the low steels, low carbon steels, I should say. You don't get this cracking problem, but when you get into the higher carbon metals, that introduces itself, and that's where you may have to heat the metal. So sometimes we use heated coils. In the older days, we used to use the oxyacetylene torch and kind of heat it up and relieve what we call annealing of the metal while it's cooling. So the other thing that we use it for is eliminating moisture. When I was on high-rise buildings and I was welding, we would take the oxyacetylene cutting torch and we would heat the weldment up that I was going to weld before I heated it up. I mean, it had some moisture, so you'd have some a dew point in the morning. So there'd be some moisture on the weld. You don't want to weld over water. So we would heat it up, remove the moisture, and then actually start the welding process itself. The other thing that we use it for is heating and bending. Several times, I mean, I can't tell you how many times where we've had bent metal, where obviously the metal was straight at one time, but there was some damage. So now it's bent, and we would take the oxyacetylene torch and we would heat the metal up in this zone right here, and then we would apply some wet rags, and we would get some wet rags and apply the wet rags onto this side. You can see possibly that if I applied the coolness on this side, it would probably, the bending would get worse, and it would. But if I applied the coolness and that on this side, it would actually start to straighten out. And it would take a few times, but eventually it would straighten itself. Just by heating it up with the oxyacetylene torch and cooling it down. It's quite an amazing thing that can happen. And I was on a job site where the crane operator had the lid open and drove by, and a tree hit it and smashed the metal hood, if you would, of the crane. A glass broke and all that. He was devastated, thought he'd lose his position there with the company. But we removed the hood, and all it took was just a flat plate. I had a flat plate on the back of the welding truck, and I just heated it up with the torch. And I used another piece of metal, flat plate down, and I just worked at it. And kept heating it up, and I straightened out the whole hood. We ordered another piece of glass, and we installed the glass, and we were good to go. So that was all done with the oxyacetylene torch. So the other thing to tell you that I wanted to mention at this time is that you can't say anything good about a world war, but you can see that this was right at the turn of the century, right? Right at 1900. And so this new process is entering into the industry. And of course, World War I comes around, 1914 to 1918, and they start seeing a use for this. And they started looking at the possibilities and what we can do with it, started seeing the feasibility aspect of it, but didn't really catch on yet. It was after that, and things started to build within the industry. The experts, engineers started to look at the possibilities of it. But that was really the start of what this process can actually do. And at this time I wanted to start talking about where we get the oxygen and where we get the acetylene for our usage for oxyacetylene. So with oxygen was discovered in 1774 by two gentlemen, Priestley and Scheele. It's used quite a bit in the industry. I wanted to say about a couple ways of that we get the oxygen itself. Oxygen is a gas element that these two folks discovered. And how do they get it? Well, a couple different ways. I can turn this over. One way is through a chemical method. It's a Brin process, and they'll find a chemical that has a chemical compound that has a lot of oxygen in it, like barium dioxide. And they would use the Brin process and try to extract the oxygen from it. Again, this is done in a laboratory, and it's a very expensive method, not quite applicable to the welding industry. Here we use the electrolytic. Electrolytic was discovered in 1800 by Nicholson and Carlisle, where a current is sent through water, and water in essence is H2O, hydrogen and oxygen. And the hydrogen is given off, you have a positive anode and a negative cathode, and the oxygen is given off on the positive, and the hydrogen is given off on the negative cathode. But it's a way of collecting oxygen. Again, done in a laboratory, very expensive, not an easy way to collect it. But by far and large, and to this day, the way that we get oxygen is through the liquid air process. The liquid air process, it was discovered in 1892 by a gentleman by the name of Parkinson. And the way we get the oxygen is that the air is actually liquefied. So, again, I have to turn this back around, but I think it'll be worth it describing this to you. But our breathing air, the air that we're breathing, is 78% nitrogen, 21% oxygen, and 1% everything else, including helium, argon, CO2, and all the other various gases. This 21%, a lot of people don't know that we have 21% air, 21% oxygen in our breathing air. And those of us that go into confined spaces, I can tell you that right at about 19.5% oxygen, it's like a fight or flight enters into the body. You have to move. And I know that because I've been in confined spaces and I've watched the gas meter. And right about that time, the body tells you that, you know, hey, I have a lack of oxygen going on. So you have to move, you have to do something. But obviously the majority of it is the nitrogen gas at 78%. And this liquid air process, what it does is it takes our breathing air and actually liquefies it. And by liquefying it, what you're left with, obviously, is with the liquefied air. Let me say something about that. I'll give you an idea of how this goes. Air is drawn into huge containers known as washing towers, where the air is purified of CO2. The air then passes through 3 oil purging cylinders that removes oil and water vapor, and then it goes into drying cylinders. Then the dry, compressed air, the breathing air that I just talked to you about, is then cooled and allowed to liquefy. The key of this is that the nitrogen boils at a much cooler temperature than the oxygen. The nitrogen boils at minus 320. So what they'll do is they'll slowly bring the temperature up. They'll boil all the nitrogen off and collect it, because nitrogen is used in the industry. And then they're, for the most part, left with oxygen. And the oxygen boils at minus 296 degrees Fahrenheit. For our welding use in the industry, we only use 99.5% pure. Any of the oxygen cylinders, anything that's used for any cutting or welding, it's 99.5% pure. Now, they can put it through additional filtering processes. Obviously, for the medical industry, you're up to 100% oxygen. And that's much more expensive process, much more filtering goes on, and so that's used for medical use. But for the welding industry itself, we only use 99.5% pure. So that's, for the most part, what I wanted to say about the oxygen. For the acetylene, and by the way, for both of these, we don't call this, even for the oxygen, we call it oxygen whenever we're talking about it. We don't say air, turn on the air. We say turn on the oxygen. And same thing, we don't say turn on the burning flame or the one that's flammable. We address it and talk about it as acetylene. So let's talk about acetylene. Acetylene was discovered in 1836. The guy's name was Edward Davy. And acetylene is a hydrocarbon. A lot of gases are hydrocarbon. This one happens to have the highest amount of carbon, but it's a hydrocarbon, C2H2. It's got 92.3% carbon and hydrogen, 7.7%. Let me give you an idea of some of the hydrocarbon gases in the industry itself. MAP gas, that burns at 5301 degrees Fahrenheit. Natural gas is a hydrocarbon that burns at 4600. Propane, 4579 degrees Fahrenheit. Propylene, 5193. Butane. And then the industry, what they did is they started mixing some of these gases together and they started developing their own. Propane, butane, butadiene, methyl acetylene, propadiene, those were all hydrocarbons. And then they developed this whole string of gases called MPS gases, where they actually mix some of these hydrocarbon gases together, and it just has a proprietary name to it. And I'll give you some of the names of them: MAP gas, ChemiClean, Apache gas, FG2, Gulf HP, Flamex, High Temp. So that's just to name a few of them. So a lot of these hydrocarbon gases are out there. However, the one that we're talking about is acetylene. And for the welding industry, for the welding here at Mount San Antonio College, we're using acetylene gas. I did work at a company when I was at the nuclear plant in San Onofre, and there was a company just designated only using MAP gas because the gas was cheaper, and they had a few hundred welders on site, so they were looking at the cost. The only thing is, MAP gas burns at 5301, where the acetylene gas, as we talked about earlier, is at 6300. So right in there, 6,000, depending on what kind of flame, but it reaches 6,300 degrees Fahrenheit. So it's a hotter gas. And my company that I was working with, we only use acetylene, and that's what we're using here at the college. So how do we get the acetylene gas? It's made by smelting coke and lime, which means just burning together coke and lime, and the result of that is calcium carbide. And it's the calcium carbide that is the key for this acetylene gas. The calcium carbide is mixed with water, and when you mix calcium carbide and water together, the acetylene gas is given off and it's collected. When they make the calcium carbide, you can buy it in 100-pound drums. So I'm hoping that you can see this okay, but when you buy it in 100, they sell it in different sizes. So the lump is 3.5 by 2 inches, egg is 2.5 by 1/2, nut is 1 1/4 by 3/8, quarter is 1/4 by 1/12. So you can get it in smaller pieces, if you will. And what they're really saying is that when you buy the lump, right, it's going to be a piece like this. That means that there's no piece larger than 3.5 inches, and there's no part of the piece of calcium carbide narrower than 2 inches, which would be here, 2 inches. So obviously this would be larger pieces, and then the pieces would be getting smaller as you, and they have smaller bits and pieces than this that I've listed. But I just wanted to give you an idea of how the calcium carbide is sold in the industry. You might recall, back in the day, they used to use the calcium carbide with water dripping for the miner lamps back in the day. And back then they didn't have gas detectors where they would tell you how much oxygen. So, the old stories of the canary, in the mines, they would have a canary there. If somebody looks over and sees the canary kicked over, they know that there wasn't enough oxygen in the room, so everyone would leave. Where nowadays we've got sophisticated gas detectors that would tell us that information, so if we needed to leave a confined space, we could do that. But back in the day, they used to light the miner lamps with the calcium carbide where it would slowly drip, and it was lit that way. Where now, obviously, we're using batteries for situations like that, and it's much safer. But I wanted to tell you about the gas itself. By adding 1 pound of calcium carbide to 1 gallon of water, the water temperature increases 90 degrees Fahrenheit. So you can see the reaction by just drying. And of course, when they do this and they make it in the industry, they have a vat of water and they just drop in a measured amount of calcium carbide into it and obviously collect the acetylene gas. But by doing that, the water temperature increases. The nature of the gas itself is quite interesting, and that's what I wanted to talk to you about. One is that it's odorless. I'm sorry, not odorless. It's colorless. It's a colorless gas, but it's got a nauseating odor to it. That's one of the things of the gas is that someone can be using the gas, and if they aren't actually burning the flame, you can smell it. And it's not an odor that was induced into the gas. It's a natural odor of the gas just being dissipated into the air. So it's a very distinctive, nauseating odor. Literally, if someone is welding here and they're not, the gas is just burning in the air, I can walk by and I can smell it. It would stop me immediately, and I would go over and try to find out where the acetylene gas was leaking. So I wanted to talk to you about the nauseating odor, and that obviously it doesn't have any color to it. But the most important thing that I want you to know about this lecture is that the gas becomes unstable above 15 pounds per square inch. So if you look on the regulators at your stations where you're at, you'll see that after the 15, so you'll have pressure 0, 5, 10, 15. But after the 15, you're going to see a red zone in the actual, so here's the gauge, 0, 5, 10, 15. And obviously you have a needle that would move in the dial here on whatever the pressure is at. But after the 15, you're going to see a red mark on the regulator. That's telling you that this needle should never go above 15. What happens is that the gas itself becomes unstable above 15 pounds. The hydrogen tries to separate itself from the carbon. Temperatures increase and pressures increase. You can have a spontaneous combustion above 15 psi. So what I'm suggesting to you is that at no time should the needle on the regulator be above 15 psi while you're using it. Now here at the welding lab, we actually have a heavy-duty regulator at the cylinders, and we set that pressure less than 15 psi. So no matter what you try to do with your regulator at your station, you couldn't get it above 15 psi. So we're safe here working. However, you need to know that the acetylene gas should never be used above 15 psi. The other thing to tell you is that usage of the acetylene gas above 15 psi, its production is prohibited, by the way. You cannot produce it at a greater pressure than 15 psi. Also, it's illegal by the UL, by the Underwriters Laboratory, which is an insurance company, fire and accident. And so it's a very serious matter, something that you should know that as you're working in the welding industry, to never have the acetylene rise above 15 psi. Last thing I wanted to talk to you about is when they first started making acetylene, they made it at very low pressures. It was less than 1 psi. They would actually have on-site generators on a project, on a work site, and they were producing it at the site, and they would run hoses out of the generator at less than 1 psi. And they had special torches, so they actually had specific torches. When we talk about torches, I'm going to talk to you about the injector type torches that they had to use for these less than 1 psi type acetylene type torches. But they don't, we don't do that nowadays. We use medium pressure type torches, and that'll be part of that lecture when I talk to you about it. So there's two ways where you would have water to the carbide where you just have water dripping on it. And those days are mostly dissipated. Those were back when the miners were using them for their headlamps. But by far and large nowadays, the acetylene is made by carbide to water, where they would have a container, a tank of water, and then just have a measured amount of the calcium carbide and just drop it into the water, and then have a collection system to collect the acetylene gas. So I think that's where I'm going to complete this lecture. Next week we're going to talk about cylinders and how they're used in the industry and how we work with them. So it was a pleasure to have you listening, and we'll talk to you next week.